So we're picking up where we left off. We're talking about the different types of covalent bonds. So covalent, again, means sharing of electrons. And here we have our polar covalent bond, which again, still sharing. So we have oxygen and two hydrogens. So we're looking at a water molecule, still sharing, but oxygen hogs a little more. So my analogy I think of for this is imagine you have one atom, in this case, I have sort of a strong man representing it, who has a lot of protons, so very, very strong. But you have another atom who's strong too. You know, it's got a lot of electrons. It's still hanging on there. It's not giving away its electron, but it's just not as strong. So if we had sort of a football player and a strong man and they had a tug of war, what's going to happen? Well, it's not going to be an easy win, but the strong man is probably going to have a little bit more pull. He's going to do a little bit better. So the electron moves a little bit more towards him. Atoms have the ability to make multiple covalent bonds, so share multiple pairs of electrons. When you see it represented in a molecular formula like this, or rather, sorry, I apologize, this is a structural formula. What it means is this line represents a pair of electrons being shared. So that means I'm looking at my hydrogen bond right here. It means that one hydrogen is contributing one electron. The other hydrogen is contributing one electron. So we have two electrons bouncing back and forth between these two hydrogens. Now, hydrogen only needs two because it's just filling up that first shell. So these are happy hydrogens. Oxygen, however, wants some more electrons. So what we have here is we have two covalent bonds that have formed, meaning we have two pairs of electrons. Your oxygen on your left gave two, and your oxygen on your right gave two. So now we have four electrons bouncing back and forth between these. And nitrogen over here, this represents a total of six electrons, or three pairs, each nitrogen contributing three to form a triple bond. Covalent bonds are your strongest bonds. The more covalent bonds you add, the more strongly attached those atoms are to each other, meaning the more energy it's going to take to break them apart. This becomes tremendously important when we start looking at how elements, which are essentially the building blocks of life, have to cycle through an ecosystem. If it costs more energy to break it apart, then you're going to need some process or some molecules that are going to help this process along. The last type of bond we're going to be responsible for are ionic bonds. This is when one atom transfers its electrons to another. So we're no longer covalent, nobody's sharing anymore. Just one electron straight up gives its electron away to the other one. Now, you may be thinking, where's this bond going to form? If one just pops off an electron and sends it over to someone else, why are they attracted to one another? And it goes back to our magnets. Opposite charges attract. The bond is due to the fact that when an electron is given away, that atom is going to change its charge. The atom that picks up the electron, it is also going to change its charge. So since these two atoms are going to end up oppositely charged, they're going to be attracted to one another. So the classic example we look at for this is table salt, so what you eat on your food. In this case, we have a sodium, which is Na right here, has one electron, just one measly electron in its outer shell. If it gives that away, notice that next shell underneath it, it has 8. That is a happy sodium right there. It's got 8 electrons in its outer shell. So it desperately wants to give that one outside one away. Chlorine, on the other hand, has 7 in its outer shell. It just needs to pick up one. So when you put sodium and chlorine together, they are tremendously reactive because the sodiums just start giving away electrons as they possibly can, and chlorine starts stealing electrons as fast as they possibly can. What's going to happen is, skip that one for a second. So what happens is when sodium gives it away, it's going to become positively charged, chlorine picks it up, becomes negatively charged, and the two are attracted to one another. The way I think about this is if you had one really strong atom and one really weak atom, so if you had a tug of war between a Girl Scout and a strongman's going to win, so he's going to get the electron. So that means one atom is just going to take this electron from the other. So atoms that give up or gain electrons become charged. And we call these charged elements ions. And ions have a very important biological role, and we'll talk about what that is. So ions are hugely important to us. The atom that's going to give up an electron becomes negative. Atoms that gain electrons become negative. This gets a little confusing for people because you have to remember electrons are negatively charged. So if you have more electrons, you're more negative. So it's this weird idea where you're gaining something but being more negative. So you got to remember that. Atoms that lose electrons are going to become more positively charged. Now, as far as this is a preview of coming attractions for us, where I want to show you guys kind of how this is important. So ions are actually used, so our nervous and muscular systems communicate with one another using charged elements. So what we actually have is we have drinks like Gatorade, and we call the ions that we put into our Gatorade electrolytes. So if you work out for a really long time, you might start to get shaky muscles. Sometimes what's happened there is you've depleted all of the ions, so your muscular and your nervous system are no longer communicating very well to one another. Specifically, they use a calcium ion, so calcium can become positively charged. It actually is a 2+ charge, so it loses 2 electrons. And your muscular system needs calcium in order for it to contract, in order for your muscles to work. So what happens is as it starts to run out of its salts, out of its calciums, your muscles will get a little shaky. If you drink something like Gatorade, it's meant to replace some of those charged particles. What's important for us to realize, though, is that Gatorade is not special. Electrolytes are not special things. You could easily take a glass of water and pour a tablespoon of salt and a tablespoon of sugar in it, mix it up, and you would feel just as good afterwards. Probably wouldn't taste as good, though. All right, so what we're going to do now is we will pause here, make sure your notes are completed. Your homework is posted in Google Classroom. See me if you have any questions.